First, thank you everybody who came to our session. We were a small but powerful group. I'd also like to thank my Indian counterpart, Sydney Lobo, for facilitating a fantastic discussion. We were talking so much and trying to flesh through ideas, we didn't actually end up with slides, but the theory being that you're actually going to listen to us more, perhaps, and we won't be stuck to the formal ideas that are up on the paper.
Yeah, and just to tell you, the discussions were so intense that we were reminded twice that, we had to go for lunch. So
we're reminded twice, yeah. They basically shuttled the entire group downstairs.
Okay, so we were discussing the electricity grid. And first and foremost, we will ask the group that let's kind of define what do we mean by the electricity grid? Or, what do we define the grid as? So the point that was mentioned is from the point of generation to the point of consumption. That was defined as the grid. And further down, we broke it into, the main transmission grid and then the distribution grid. Now, the transmission grid is composed of, transmitting power at 400 kVA and above. And it has intermediate, transformers and step-down locations, which then bring it down to a voltage which is further distributed. In India, the main grid, or this transmission grid, is controlled by Power Grid Corporation of India. And as on today, or as on March 31st, they have already laid about 100,000 circuit kilometers of transmission network. So the transmission network does exist, and they today transmit about 28,000 megawatts through that. And by 2017, they plan to take it to about 65,000 megawatts. There is 99% availability in the transmission network. And since it is controlled by a public sector undertaking under the Government of India, we thought that, we'll keep them aside. And we focused more on the distribution network. And what was the next point that we had?
Rural versus urban.
Yeah, so that's how we split it up. And we also thought, today, since there is a demand-supply gap, and even though the grid is available, maybe to the last mile of certain villages, maybe not all, but the rural needs are not met because there is a huge demand-supply gap in terms of the generation to the demand of power. So it's not that the grid is not doing its job. There's no juice to flow through the grid. And so we thought that rural and urban were actually separate issues as on today, but in the long run, when there is sufficient power available, we thought that the issues that will be faced by the rural and urban sector or urban population would be pretty much the same. So that's how the discussion focused on a futuristic site. And so some of the things that were identified and were of top concern were, one was power deficit, of course, that the generation team would take care of. And there is theft or loss in the transmission system. And because of, certain issues, there is a lot of load shedding. Okay, and based on this background, some innovative ideas were discussed, which Emily is going to elaborate further.
Yeah, thanks. So the discussion was largely around trying to address these challenges and ideas. And there was a word that came up in about 5 different ways at least, and it was microgrid, grid and grid, mini grid. Let me see what else I have. And we ended up just calling them cells. Basically things that can operate fairly autonomously, but, in the future would be communicating with a cluster or a honeycomb in a honeycomb format. And then that really got the group going because then it was like, what do we want this grid to have? What does it need to do? And so first it needs to have situational awareness just within itself and broadly. Even in the States, if you lose your power in your home, the utility doesn't actually know it necessarily unless you call and say, I'm on this street and I don't have my power. And that sort of thing is also similar in India, where people don't actually know where the thieves are hooking the line and where these losses are occurring. And so that kind of thing started a discussion about sensors, and that sensors right now are, they need to be more communicative. So they need to have 2- or 3-way communication. So much smarter grids or power electronics and operation. So there's and so that kind of goes into the smart grid idea too, where you have meters and sensors. What else? And then the optimization within its cell, and then between cells. And so then as we started talking about cells and the idea that, maybe in rural communities, these cells will be very, if it's a biogas cell or if it's a PV cell that's predominant, if these are the predominant forms of generation, they're actually going to be pretty rough in terms of providing ancillary services or reactive power. So then we started talking about sort of prioritizing or grading the cells, and then this also talked about different levels of grid, and we described it as economy to first class grid, and you wanted to know if that was a patented word already, but basically these levels of grid that could describe sort of, one, the level of service, whether it be just basic lighting, or 2, UPS type, where you have to provide 24/7 to hospitals and emergency services. So for these cells to interact with each other, there's a lot of algorithms and optimization that occurs. And while we agreed that that doesn't exist now, it's something that can be developed. And the technology, in terms of the hardware, also exists for the most part. I mean, it's tractable within the next 10 to 30 years. Something that got a lot of excitement as we talked about implementing these visions was the community, sort of the culture of India. But it was agreed, hands down, that this has to occur from the individual and community level. If this came down from the utility and said, we have this program for load shedding, nobody would sign up. It had to be, this was a new term I learned, like a goon. And basically this person who comes around and starts negotiating with people to say, if, this is sort of to address the urban aspects of load shedding and aggregating loads to work as a sort of virtual power plant. But if people said, give me your critical loads that I can back off during peak times, so that you don't necessarily lose your power, but you can lose the appliances that you don't need to have operating right now. And that way, instead of a whole region being blacked out, then instead, your dishwasher stops, or maybe the temperature in your house goes up 2 or 3 degrees, but you still, for the most part, have power in your house. So there was a lot of discussion that these weren't necessarily technology issues, but that it could be addressed in different various business models. But there was a lot of innovation that could be possible there. Am I missing anything? Okay, I was expecting anybody from the group to chime in. And lastly, we let ourselves go very far out in thinking about a future vision of the electric grid, out of context of India and the US, and talking about wireless transmission of electricity. So being in a situation where you could have big, areas that are generating and have solar at one, somewhere always has light in the globe. So if you had the area covered in Australia, that could serve a certain area out in Nevada, or actually Nevada probably wouldn't, somewhere else that needs the light. So you would have these big, receivers and transmission through wirelessly, or maybe in the interim through lasers.
Just to explain what Emily is trying to say, I mean, this was inspired by Professor Bruce yesterday, where he showed just a small square, saying that this square can meet with today's solar efficiency, it can meet the demand of the world. So we said, okay, if we have a similar size solar plant in Australia, one in Nevada, one maybe in Saudi Arabia, and one somewhere in the South African continent, all these places, sometime or the other, in the 24 hours, at least one location will have the sunlight. Now, how do you get that across to the globe? So if you can have wireless transmission, Australian power, when there's sunlight over there, can feed the full globe. And then when the sunlight is in the mid portion, it can feed the others. When it's in Nevada, you feed the rest of the world. So there's no need of power lines. It just everything goes through the air. Of course, the key is how do you send it out and how do you receive it without, kind of making a turkey out of someone in between.
Yeah, and then if we actually did have to step back into the context of the grid that we have today, then there was talk about superconducting transmission lines, reduced HVDC transmission, and solid-state power electronics. That's it for us. If I missed anything, I want the group to chime in.
Okay.
Yeah, that was mentioned too. Yeah, I mean, there was discussion about storage, the need that, as these cells interact or within a cell, that there might be storage needs, and that was, there was the conventional things that we've talked about, like batteries, but then, load shedding and aggregating loads in a way is also a way to do that.
Yes, over here.
With the concept of these cells, what happens is you don't have to look for grid storage. The storage problem then again becomes distributed, because you have now cells, each cell having its own variation and own load demand and discrepancy in energy. So the storage problem now becomes a distributed problem. So one could actually use a lot of the technology which is existing today to do a distributed storage. So that's how the storage, and the idea was that since these cells eventually will be managed and run by small entrepreneurs who would then buy and sell energy using sort of a mutual fund concept. So the negotiation part which you mentioned was about the owner negotiating with the cell constituents, saying that you give me so many units, and then that owner goes and negotiates in the electricity market. The storage starts being brings in an opportunity cost and starts paying for itself. So now we are wondering how do we manage storage and energy balance and so on. So the storage becomes part of the whole solution, that you can actually store energy and play with the market to get the costs back.
Okay, thank you. Yes, back here.
Hello? It's okay? Yeah, when you're talking about wireless transmission of energy, I think what people also need to think about is when is the Supreme Courts of countries going to enter the whole this business? See, because in Kerala, for instance, we've seen that entire species of birds have vanished. Okay, when it starts hitting genetic biodiversity and starts killing species, at that time you got to stop at a certain point where, transmission of energy by electromagnetic radiation, that's something that people need to think about. Because I think this is going to finally become a matter for the Supreme Courts of countries.
Okay, and over here.
This question is basically directed at Mr. Sidney Lobo. Typically, this time difference between the western and the eastern regions of India, like northeast is typically hydro generation. Northern India also has some parts of hydro, and we have this imbalance in loads across. Has ever at a national level been pumped up storage been tried?
Yes, pumped up storage is being tried here itself, maybe about 900 odd kilometers from here. And we do it. We've got a 150 megawatt pump storage facility. So during the daytime, we use the lake waters, generate power, and at night when we just have to idle, we pump it back up. And so pump storage is something which is being done in India at the moment.
But it's not done at a national level, that's what you're saying. Where typically, let us assume the northeast region, which is totally hydro-driven, and when there is demand in the night from the urban centers of north and the west, and some parts of the south, can that be used across your HVDC lines to feed the grid across? Or
See, it all depends upon what's the cost of power. If the power cost at night is really low, then it makes sense to pump water back on top. If the power cost is expensive, then it just doesn't make sense. Secondly, in India, we also have this issue of water rights. Okay, so what water has to be released in the generation space of hydro, you can release, or you have to release X amount of water every day. irrespective whether you use it for generation or not. You cannot release more, you cannot release less. So your capacity factor is frozen because that water goes downstream for irrigation or as utility or just domestic water. So those restrictions are there, as a result of which you cannot play with hydros too much. And that's the reason why hydros are not used as base load. It's only used for meeting to meet peaking power.
Okay. All right. Yeah.
And although you mentioned you didn't touch the transmission grids, but is there any merit in high voltage DC?
In high voltage, yeah, go ahead.
In the US or
Here.
In high voltage DC in India, we do have HVDC right now. I mean, just a couple of lines. The grid which is above, or the north, central, eastern, and western grid is one grid. And then you have the southern grid. So we have these two grids. They are linked with a HVDC system, but the HVDC is actually weak. And HVDC makes sense if there is a transmission distance of at least 800 kilometers and above. So that's the reason. If HVDC the cost can be brought down, then it makes more sense because your losses are much lower.
Okay. All right. Thank you.
If you have two energy-rich regions, and there is really a value of exchanging energy between the two regions, even a short distance HVDC can be used. The example is Itaipu power station between Brazil and Uruguay. It's on the Itaipu River. One country is 60 hertz, another country is 50 hertz. It's a very short distance HVDC link. The additional power is exchanged between these two. So it makes sense when the two regions are very...
That's the economy part.
Yes, that's the economy part.
Here we get regulated.
It's always about...
Yeah, it's always about the money. I mean, if the regulator is saying you can't do it, you can't do it.
One more point about HVDC. As you start doing more and more offshore power production, in offshore HVDC becomes more economical beyond 50 kilometers itself. So any offshore, because the cables going underwater, the inductive effects are much more because it's the water and not air. So for offshore lines, 50 kilometers plus are going to be economical. So as we start generating offshore solar or wind or whatever, that will be another opportunity for HVDC.
Okay. All right. Thank you very much. Great job.